Welcome to our continuing discussion on natural convection. I had explained to you in the previous class what is meant by natural convection. If you have a heated object in water or in air, for example, the fluid close to the heated object has a lower density than the ambient fluid. Lower density means that it has due to the buoyancy effect, it is going to rise. As it rises, it carries along the heat with it, and in order to replace that hot fluid, cold fluid from the ambient has to come in to replace that. It gets heated up in turn and then it rises. In this case, the fluid flow is actually caused by the body force density due to the gravitational acceleration. That in turn is caused by the change in density close to the fluid, that due to the change in temperature. Therefore, the temperature difference causes a density difference, which causes a fluid flow, which causes an enhanced heat flux, and that is what we were trying to calculate in the previous lecture. We had started off with the steady state temperature equation and the momentum equation, the mass equation and the momentum equation. Okay. In this, we had subtracted out the hydrostatic equation in the absence of flow, which should be valid far from the object, because far from the object the density is a constant and the temperature is a constant, and therefore, these hydrostatic conditions should apply far from the object. And once we do that, we get a body force term that is basically the difference in density between the local position and the density far from the object. Okay. So, the body force is dependent upon the density difference. We had simplified the equation. The density difference in turn depends upon the temperature difference. We had assumed that that was a linear relationship, okay, with a thermal expansion coefficient beta. And I had argued in the last lecture that beta is actually numerically small in most fluids of everyday use. Beta is of the order of 10 power minus 3 in air and about 10 power minus 4 in water. And for this reason, in real applications, the change in density is much smaller than the average density of the fluid. However, the force due to the change in density has to be taken into account. Okay. The change in density can be neglected in the mass conservation equation, the inertial terms in the momentum conservation equation. However, it has to be taken into account, because without that there will be no force which is driving the flow. The linear approximation is valid so long as the temperature difference is small compared to the absolute temperature. Under those constraints, we had derived a set of equations, okay, which we had called the Boussinesq equations. Okay. In the temperature equation, we assume that the thermal diffusivity is independent of position or independent of temperature. Mass conservation equation reduces to divergence of velocity is equal to 0. Okay. We assume that the density variations can be neglected. In the momentum conservation equation, in the inertial term as well, we assume that the density is a constant, it is equal to rho infinity. In the viscous term, the viscosity is also a constant. Density variations due to temperature variations come in to the body force term here. Okay. And this is what couples the momentum equation with the temperature equation. Okay. So, the temperature affects the momentum equation through the body force, okay, which is because of the temperature difference, and the velocity affects the temperature equation due to this convective term. Okay. And that is why there is a coupling between the temperature field and the velocity field. Velocity field is generated by the density difference due to the temperature change, and that velocity field convects the temperature along with it. We were trying to find out what is the magnitude of the velocity in that case. Okay. We had scaled all the positions, the coordinates by the characteristic length, the characteristic length of the object, the length of the flat plate or the diameter of the pipe or some other characteristic distance. Velocity, we did not yet have a scale. Okay. The temperature we had defined as the change in temperature between the local position and T infinity divided by the temperature difference between the object and the ambient. Okay. That is a natural choice as we have seen. And we also defined a gravitational acceleration as the product of the magnitude of the acceleration times the unit vector. Unit vector defined in this way is dimensionless of unit length. Okay. It is a vector of unit length and it is dimensionless. Okay. So, we had inserted this into the equation, and by balancing convective terms with the body force term, we had found out what is the scale of the velocity. Okay. So, u was equal to beta g delta t into L square root of. Okay. That was the magnitude of the velocity. Okay. Now, I can use that magnitude of the velocity in order to find out what are the other terms in the equation. Okay. So, now the equation for the temperature field becomes of the form is equal to alpha by u L. Okay. Okay. And the momentum conservation equation, okay, the mass conservation equation just becomes the divergence of velocity is equal to 0. The momentum conservation equation becomes u dot grad u is equal to of the dynamical pressure plus mu by rho infinity u L. Okay, this should be velocity, should be a vector here, I am sorry. Okay. And then I have this last term on the right side, which is plus rho infinity beta g into T naught minus T infinity, okay, divided by rho u square times T star g hat, where g hat is a unit vector. Okay. This entire factor here is 1 because we have balanced the rho u square with this body force term. Okay. So, that entire factor is 1. What I get here are two numbers, dimensionless numbers. One is the inverse of a Reynolds number based upon u, the other is the inverse of a Beckley number based upon u. Okay. So, let us look at what those numbers are. Okay. So, to recall, the value of u is equal to root of beta g delta t into L. Okay. And my equations are of the form u star dot is equal to alpha by u L into and I do not know if I scaled the pressure previously, but I should. Okay. So, let us go back and correct the pressure scaling. Okay. Okay. If I divide by rho u square by L, then I will get 1 by rho infinity u square, okay, for the pressure term here. Okay. And therefore, I have to define the dynamical pressure, scaled pressure as P d by rho infinity u square. Okay. Okay. And defined that way, the pressure term becomes dimensionless. Okay. So, that is the balance equation. Okay. So, this thing is 1 over a Reynolds number. So, let us look at this term here, okay. Rho infinity u L by mu. Okay. This is going to be equal to rho infinity into L into This dimensionless number is what is called, it is actually the square root of the Grashof number, okay. The square root of the Grashof number, okay, where the Grashof number is defined as rho infinity square L cubed beta g delta t by mu square. Okay. It is the square of a Reynolds number based upon the characteristic velocity due to convection. Okay. It is the square of a Reynolds number based upon the characteristic velocity due to convection. It can also be written as L cubed beta g delta t. Okay. By kinematic viscosity square. Okay. Okay. So, this term is actually one by Grashof number to the half power. Okay. The Grashof number to the half power in the denominator in this case. Okay. This second number here, okay, is the inverse of a Peckley number, okay, based upon this characteristic velocity due to the natural convection, due to the temperature change. Okay. This number here u L by alpha, okay, okay, is going to be equal to L root of beta g delta t L, okay, by alpha. Okay. This number will basically is equal to the Grashof number times the Prandtl number. Okay. This number is basically equal to the Grashof number to the half. So, if I take this Grashof number to the half, okay, if I take this Grashof number to the half and multiply it by the Prandtl number, okay, you can see that this will be equal to rho infinity L u by mu. The Prandtl number is the ratio of momentum diffusion and thermal diffusion. Okay. So, this is equal to mu by alpha. Okay. So, this I am sorry, the ratio of momentum diffusion and thermal diffusion. So, it should be the kinematic viscosity. Okay. So, this is equal to L u by nu into nu by alpha. Okay. Is equal to L u by alpha. Okay. So, this number here is just the Grashof number to the half, which is the ratio of convection and momentum diffusion, times the Prandtl number, which is the ratio of momentum diffusion and thermal diffusion. Okay. So, this is Grashof number to the half times the Prandtl number. Okay. So, once you do that, you get the dimensionless equations. Okay. In this case, I will write this as Grashof number to the half times the Prandtl number, where my definitions for the Grashof number is equal to by mu square is equal to L cubed and the other term is the Prandtl number, which is just equal to nu by alpha. Okay. So, therefore, there are these two dimensionless numbers that come in, okay. One of them multiplying the viscous term in the momentum conservation equation, the other multiplying the diffusion term in the equation for the diffusion coefficient. Okay. And traditionally, the Reynolds number based upon the natural convection velocity, okay. The Reynolds number based upon the natural convection velocity is written as Grashof number to the half power. Okay. Traditionally, it is done that way. That is the reason that we have chosen 1 over gr to the half. If you are doing it for the first time, it would be more natural to define a dimensionless number as the square root of this, but this is the way it is usually done. So, we will use the same sign convention, the same definition. What are the magnitudes of the Grashof number in normal applications? Okay. Even if we take a relatively small system, okay, Let us assume that the pipe, for example, had a length of approximately 1 centimeter, okay, which is equal to 10 power minus 2 meters. Okay. Beta we will assume is equal to 10 power minus 3. Okay. Delta t is of the order of 10. Okay. Beta has to have dimensions. Okay. Kelvin inverse, and delta t is of the order of 10 Kelvin. Okay. What is the Grashof number? Okay. Grashof number is L cubed beta g delta t by kinematic viscosity square. Okay. For gases, okay, L cubed is 10 power minus 6 in meters. Okay. Beta I told you is of the order of 10 power minus 3, and delta t is of the order of 10 Kelvin, right. So, I get 10 power minus 3. Okay. G is 10 in meters per second square, and delta t is of the order of 10. Okay. The kinematic viscosity for gases, we had seen that when we did diffusion. Kinematic viscosity is of the order of 10 power minus 5 meters square per second. Okay. Kinematic viscosity divided by the 1 over kinematic viscosity square is of the order of 10 power minus 5 the whole square, okay, which is 10 power minus 10. Okay. And if you write down all of these numbers, okay, you get 10 power 3. Okay. Even when the temperature difference is small, okay, of the order of only 10 Kelvin, the expansion coefficient is small. Okay. The fact that you have a kinematic viscosity and the length scale is relatively small, okay, it's of the order of a centimeter. The fact that you have a kinematic viscosity in the denominator square, the square of the kinematic viscosity implies that the Grashof number is invariably going to be very high. Okay. So, these kinds of parameters are what are seen in gases. Okay. In liquids, okay, if I take the same length of 10 power minus 2 meters, okay, beta in liquids is still smaller, 10 power minus 4. Kelvin inverse, okay, and delta t is equal to 10 Kelvin. Okay. In liquids such as water, the kinematic viscosity is actually 10 power minus 6. The dynamic viscosity is 10 power minus 3 and the density is 10 power 3. Okay. So, you will get 10 power minus 6 meters square per second. Okay. And if I look at the Grashof number for that, this will become length cubed is 10 power minus 6 into 10 power minus 4, gravity is 10, temperature is 10 divided by 10 power minus 12, because I have a kinematic viscosity square in the denominator. Okay. And this is of the order of 10 power 4. So, even for relatively small systems, the Grashof number is very large, and the Grashof number increases as the cube of the length. Okay. So, if I go from a system of about 1 centimeter to a system of about 10 centimeters, the Grashof number would increase by a factor of 10 power 3. Okay. So, the Grashof number is invariably a very large number, and therefore, in all of these cases, convection is invariably much larger than diffusion. When convection is much larger than diffusion, you would think that you can neglect diffusion altogether. However, the transport from the surface has to take place due to diffusion, because there is no convection perpendicular to the surface, and there has to be a boundary layer close to the surface whose thickness decreases as the Grashof number increases in such a way that there is a continued balance between convection and diffusion even in the limit as the Grashof number goes to infinity. The same procedure that we had used for forced convection, except now that we have to solve simultaneously the temperature and the momentum equations to determine simultaneously the velocity and the temperature fields. In this particular case, I will derive the equations and I will scale them. I will not solve them numerically, because the procedures for numerical solution we have not yet discussed in this course. It turns out that you have to have ways of solving the momentum and the mass conservation equations simultaneously for two components of the velocity plus the energy equation, and we have not yet looked in detail at fluid mechanics. How does one solve coupled vector equations? Okay. Therefore, I will just scale the equations, and from the thickness of the boundary layer I know that the flux goes as the gradient of the temperature, which goes as the inverse of the boundary layer thickness. From that I will get scalings for the Nusselt number as a function of the Grashof number and the Prandtl number. So, these equations that I have here, these equations that I have here, I have to write out in terms of their components. So far I have written it as a vector equation, but now I have to separate them out into their components parallel and perpendicular to the surface, and then scale the individual components. So, let us take some surface. There is some flow going around the surface. And as I showed you, for these cases Grashof number is large, convection is large compared to diffusion for most of the fluid. However, close to the surface convection and diffusion will become of equal magnitude within a boundary layer of thickness delta, which is small compared to the characteristic dimension L. The thickness is small compared to the characteristic dimension L. So, that locally over this distance delta, I can write down a coordinate system in which the streamwise coordinate is x and the cross stream coordinate is y. If the thickness is small compared to the dimension of the object or the radius of curvature of the object, then locally I can consider the system to be flat, because the curvature is much smaller than the radius of curvature is much larger than the boundary layer thickness. So, locally at this point I can write down the balance equations. I'm sorry. That is the mass balance condition. The first one is the energy balance, the second is the mass balance, and then I have the momentum conservation equations in the x and the y direction. G hat x is the component of G along the x direction. It is the component of the unit vector along the x direction. So, if x is aligned at an angle theta to the vertical, G hat x will be cos theta. And in the cross stream direction I have how to get these component equations from the original vector equation. Okay. In case you have any doubts about that, how to get the component equations from the original vector equation, please go and refer back to the lectures where I had discussed the momentum conservation equation for an incompressible fluid. These equations are the same as the momentum conservation equations for an incompressible fluid, except that I have a body force in this case, okay, because I have neglected density variations in every term except for the body force term. Okay, so, these are the original equations. Now, for this particular situation, when the Grashof number is high, okay, and the Grashof number is high, if you just simplistically neglected, okay, the diffusion term, okay, in both the temperature and the momentum conservation equations. In the case of the temperature equation, what it would basically tell you is that u dot grad T is equal to 0, which means that the temperature is a constant along the velocity streamlines. With that, you will not be able to satisfy the boundary condition at the surface, okay, and therefore, you have to consider a thin region, rescale the y coordinate, okay, rescale y star is equal to y by delta. Okay, I am sorry, I have already used y star here, so I will use another notation. Okay. Where delta is the scaled boundary layer thickness, the boundary layer thickness divided by the characteristic size. Okay. So, I have to rescale my cross stream coordinate in such a way that in the momentum and temperature equations, convection and diffusion continue to be of equal magnitude even in the limit as the Grashof number goes to infinity. We will see how to do that in the next lecture. Okay. I will continue this in the next lecture. I will rescale the cross stream coordinate by a boundary layer thickness and derive the condition for the boundary layer thickness such that convection and diffusion are of equal magnitude within the boundary layer, that is streamwise convection and cross stream diffusion are of equal magnitude within this boundary layer. Okay. So, we will continue this scaling argument in the next lecture. I will see you then.